Today, we are going to explore how to clearly communicate sequential processes. Understanding and sharing step-by-step instructions is essential in many fields, whether it's for training, project management, or everyday tasks. We'll look at practical ways to break down complex procedures into easy-to-follow sequences, making sure everyone involved can understand and follow along smoothly. This will help improve clarity, reduce errors, and ensure consistent results. Let's get started. When people talk about cars, they often focus on the design, engineering, and performance of the vehicles themselves, like whether an engine is turbocharged or naturally aspirated, or if the car has a mid-engine or front-engine layout. These details are important to enthusiasts, but they don't tell the whole story about how a car actually performs in everyday life. What really matters most is the road network, because it directly affects how accessible places are, how easily we can move around, and how efficient our travel is. Without good roads, even the best cars can't reach their full potential. The main features and how well a message passing system works don't really depend on the application code itself. While the design or content of the messages does have some impact, it's actually a secondary factor. The key element that shapes the system's performance, reliability, and ability to grow is the transport mechanism underneath it all. This is what ultimately determines how effectively the system can handle communication between processes. The actor model is a way to build programs using independent entities that run at the same time, called actors or processes in Elixir. These actors work concurrently and communicate with each other by sending messages. Each actor has its own mailbox where incoming messages are held until the actor is ready to process them, allowing them to work independently without waiting on others. This approach helps manage concurrency efficiently by keeping the actors isolated and making communication explicit through message passing. In the communicating sequential processes model, programs consist of independent entities that run at the same time and communicate by exchanging messages. The key difference here is that CSP shifts the emphasis from the entities sending messages to the communication channels themselves. Instead of each process being tied to a single mailbox, CSP treats channels as first-class objects. This means channels can be created separately, written to, read from, and even passed around between processes, offering much more flexibility in how communication is structured and managed within the system. Communicating sequential processes, or CSP, is a formal language designed to describe how different parts of a system interact when they're working at the same time. It was created by Tony Hoare in 1978 as a way to analyze and model systems made up of multiple processes that send messages to each other. This framework uses mathematics to help us understand and predict how these processes behave together. CSP is particularly useful in systems where it's important for processes to communicate clearly and coordinate their actions precisely, like in real-time or safety-critical applications. In CSP, several key operators help define how processes interact and execute. The sequence operator shows actions happening one after the other in order. The choice operator allows a process to decide between different possible actions, kind of like making a decision. Parallel composition means processes run at the same time, working concurrently. Interleaving is similar, but here processes run independently without interacting with each other. The hiding operator is used to conceal certain events from the outside environment, keeping some details private. Renaming changes event names to make processes simpler or more abstract. These operators give us a precise way to describe complex behaviors in concurrent systems. Processes in CSP synchronize by sharing events, which means they coordinate their actions to work together in a controlled way. This synchronization is crucial because it ensures the processes cooperate properly rather than acting independently or at random. However, synchronization also introduces risks like deadlock and live lock. Deadlock happens when processes are waiting indefinitely for events that never take place, causing the system to halt. Live lock, on the other hand, occurs when processes keep performing actions repeatedly but fail to make any real progress, essentially getting stuck in a loop of activity without completing their tasks. Understanding these core concepts helps in designing concurrent systems that are efficient and avoid common pitfalls. CSP supports formal analysis by enabling us to rigorously verify important system properties such as deadlock freedom, which ensures the system doesn't get stuck, live lock freedom, which prevents endless looping without progress, and communication correctness, meaning message exchanges happen as intended. It also promotes modularity by allowing processes to be defined independently and then composed together, so complex systems can be built up in a manageable way. Additionally, CSP offers a clear framework for reasoning about concurrency, helping us understand and design how processes run in parallel and interact efficiently. This combination makes CSP a powerful tool for modeling and analyzing concurrent systems. This approach forms the foundation for concurrent programming paradigms and languages like Go and Ada, making it easier to write programs that run multiple processes at the same time. It also plays a key role in distributed systems by modeling how different parts of a system interact, such as in client-server setups. When it comes to designing communication protocols, it helps ensure that messages between different components are exchanged correctly and reliably. Lastly, it supports formal verification through model checkers, which are tools used to rigorously confirm that a system meets its desired properties and functions as intended without errors. Python doesn't have built-in support for CSP like some other languages such as Go or Erlang, but it is still possible to implement CSP concepts in Python by using different techniques and libraries. Several libraries have been developed to bring CSP-like behavior into Python programs, making it easier to work with concurrency while handling much of the complexity behind the scenes. These libraries provide abstractions that let you model processes and communication patterns similar to those in CSP, so you can apply its principles in your Python projects even without native language support. CSP provides a strong framework for understanding how concurrent systems work, especially when it comes to processes communicating through message passing. Even though Python doesn't have built-in support for CSP like some other languages, you can still apply its principles using available libraries such as PyXP, or by leveraging Python's asyncio and threading modules. These tools make it possible to design systems that follow the CSP approach, enabling better management of concurrent tasks and communication between them.